In this video, we are going to be learning how to solve more complicated projectile motion problems. So here are some tips to solve these problems. First, always think of using the second kinematic. Generally, you want to use the second kinematic to find the time in one direction, so the x or y direction, and then apply that time to the other direction. You want to keep what is happening in the horizontal and vertical directions distinct from each other. Remember that there is no acceleration in the x direction, so the second kinematic will simplify to xf equals vix times t. So the final position is equal to the velocity in the x direction times the amount of time the object is traveling for. Lastly, draw stuff out. Here is sample problem number 1. King Arthur's knights use a catapult to launch a rock from their vantage point on top of the castle wall 12 meters above the moat. The rock is launched at a speed of 25 meters per second and an angle of 35 degrees above the horizontal. A. How far from the castle wall does the launched rock hit the ground? And B. With what velocity does the rock hit the ground? And we want both the magnitude and the angle there. So let's use one of our tips. Let's draw this out. So that's my lovely drawing of knights, and here's the catapult, and it is launched at this speed, at this angle. It'll make a trajectory, something like that. And we know it's 12 meters above the moat. So for part A, we want to find this distance here. And we're going to start by writing what we know in both the x and y directions. So let's add some stuff to our drawing here. So we know that the initial position in the y direction is 12. The final position in the y direction is 0. The initial position in the x direction is 0. And we're looking for the final position in the x direction. Let's make our x and y chart. So in the x direction, we can pretty easily find the initial speed in the x direction. Remember that the initial speed in the x direction will be vi cosine theta, which will be equal to 25 times the cosine of 35 degrees, which equals 20.48 meters per second. We can also find the initial y velocity by doing, this should be a y there, by doing vi sine theta, which is 25 times the sine of 35, which is 14.34. And we know the initial position in the x direction. We're looking for the final position in the x direction. We know that the acceleration in the x direction is 0. In the y direction, we know that the initial height is 12, final height is 0, the acceleration is negative 9.8. And we don't know the time in either direction, but we do know that this time and this time will end up being the same. So when the object is here in the y direction, it's also there in the x direction. So one of my tips was to use the second kinematic in one direction, use that to find the time, and apply that to the other direction. So we definitely have enough time to find how long this rock is in the air for if we use the y direction. So here's our second kinematic in the y direction, and let's plug in our relevant numbers here. And I'll need to go on to the next slide. So we've got our final height of 0, our initial height of 12, our initial speed in the y direction as 14.34. 1/2 of the acceleration is negative 4.9, and that's t squared. So then we can go ahead and use the quadratic formula to solve this for t. You should get negative 0.679 and 3.606. And we want to use this positive time here. So this time here is how long that rock was in the air for. And if we know how long it's in the air for, then we know how long it traveled in the x direction as well. So let's take a look back at what we know. Well, now we know the time. So if we apply this time to the second kinematic in the x direction, we can figure out how far it's gone. So remember, this term in the second kinematic in the x direction will disappear because it's 0. This term will also disappear because the acceleration is 0 in the x direction. And we know that Vix is 20.48, and we know that the time is 3.606. And we get that the final position in the x direction is 73.85 meters. And so this is our answer, and I can't seem to draw an A. There we go. This is our answer to part A. Now part B asks, with what speed or with what velocity does it hit the ground right there? So this will have an x component and a y component for the velocity. So let's figure out the x component first. And we don't actually have to do any math for that, because in the x direction, there is no acceleration. So the initial velocity in the x direction will just be equal to the final velocity in the x direction, which is just 20.48. Now, if we think about what we have in the y direction, we now have that time. So we can use the first kinematic equation to figure out what the velocity is in the y direction at this point here. So we're looking for VFY. VIY is 14.34, AY is negative 9.8, and T is 3.606. And the final velocity in the y direction is negative 21 meters per second. So remember, we want to find this overall velocity vector. So we've got the y component of negative 21, and then this x component of 20.48. So we want to find the hypotenuse of the triangle, and for that we can just use the Pythagorean theorem. So it's going to be the velocity in the x direction squared plus the velocity in the y direction squared, all in a square root sign. Remember, this does not need to be negative, because when you square it, it'll just become a positive. And the velocity you get will be 29.3 meters per second. Now, we also want to find this angle right here below the horizontal. So to do that, we would do the inverse tangent, because this is opposite. That's supposed to be an O, and this is adjacent. So the inverse tangent of the y component over the x component, which is 21 over 20.48. And that angle would be 45.72 degrees, and the direction words would be below the horizontal. So the entire answer for part B would be those two things I just circled. Now let's think about if these answers are reasonable. Well, 25 meters per second is pretty fast, so it makes sense that a rock could go this far. And it makes sense that it would hit with about this speed as well. All right, let's do sample problem 2. Suppose a soccer player kicks the ball from a distance 30 meters toward the goal. We want to find the initial speed of the ball if it just passes over the goal 2.4 meters above the ground, given the initial direction to be 40 degrees above the horizontal. So right away, it looks like we're not given very much information. So in order to figure out what information we actually have and how to solve this problem, let's start by drawing it out. So we just have the soccer ball launched at 40 degrees. We know that the net is 30 meters away, and it just passes over the top here at 2.4 meters. So let's also just write out what we have in the x and y directions. So we know that Vix will be equal to Vi cosine theta. The problem here is we don't have Vi. However, we do have theta, which is 40. And I always find it easier to work with actual numbers than trig functions. So I'm going to say, okay, I know that Vix equals Vi cosine 40. And the cosine of 40 degrees is 0.766. So I know that Vix is equal to 0.766 Vi. Let's do the same thing in the y direction. So VIY will equal VI sine theta. Again, we don't have VI, but we do have theta. So we'll get that VIY is equal to 0.643 VI. What else do we know in either direction? Well, we know that the initial position in the x direction, so that would be right here, is 0. We know that the final position is 30 meters. In the y direction, we know that the initial position is 0, and we know that the final position is this 2.4. What else do we know? Well, we know that the acceleration in the y direction is negative 9.8 meters per second squared. We know that the acceleration in the x direction is 0. We know, well, we don't know the time in either direction, but we do know that at this point, it'll be the same amount of time in both the x and y directions. So these two times are equal. So where do we go from here? Well, a good place to start with these is just to use the second kinematic, because what we care about most for problems like these is usually the position and the time, and the second kinematic is the most appropriate equation to use there. So let's first set up the second kinematic in the x direction. So we know that xf equals 30. This term will disappear, as will this last term here. Vix is 0.766 Vi, and we don't know t. So that's what our second kinematic in the x direction looks like. And let's see what it looks like in the y direction. So YF is 2.4, YI is 0, VIY is 0.643 VI, AY is negative 9.8, and 1/2 of that would be negative 4.9. So our second kinematic in the y direction is going to end up looking like this. Now, having two directions here is actually pretty convenient, because now what we see is we have two equations and two unknowns, which means we can pretty easily solve a system of equations. So let's identify what we have. One of our unknowns is VI. We have a VI in this equation, and we have a VI in this equation. And then our other unknown is T. We have a T in this equation, and we have T here and here in this equation. So on this next slide here, I'm going to use substitution to solve for my missing variables. Now what I'm noticing here, it'll be easier to solve for a missing variable in this x equation. And also, I think I'm going to go ahead and solve for VI, because VI, I would only have to plug it in one place in this equation in the y direction. So ultimately, as long as you do your algebra correctly, it shouldn't matter which one you solve for first. So anyway, I'm going to solve this x equation for VI. So all we have to do that is divide both sides by 0.766 t. So 30 divided by 0.766 is 39.16, and that'll just be over t, and that'll equal VI. And then we can go ahead and plug that in right there. So it'll be 2.4 equals 0.643 times 39.16 over t times t minus 4.9 t squared. Let's simplify this. So first, I could see this too from earlier. These two t's will cancel out. And then to simplify it further, we would do 0.643 times 39.16. Now I'm going to subtract 25.1827 from both sides. Then I'll divide both sides by negative 4.9. So I'll get 4.65 equals t squared. Then take the square root of both sides. I'll get that t is equal to 2.16. So now I can take this t and plug it into this t right here to get VI. So VI will equal 39.16 divided by 2.16, which is equal to 18.16 meters per second. So that did seem pretty complicated, but once we came up with our system of equations using the second kinematic, we were able to solve it pretty easily. So just keep these techniques that you've learned for these problems in mind when solving more complicated projectile motion problems.